BloombergGPT is a 50 billion parameter language model trained on about 570 billion tokens of training data, about half of which is from the financial domain. Training a language model, a very large language model, is difficult. It takes a lot of resources. Not a lot of individuals or teams have attempted it, and far fewer have given any details of the challenges they faced and the false starts they had and how they overcame them along the way. You just get kind of cleaned up results. Two projects last year in 2022 were very generous with sharing their own experiences in training the models by sharing their training logs, training chronicles. And our project benefited enormously from their sharing. And so I'm kind of appreciative of this opportunity to pay it forward by sharing with you all our own experience training this large language models with all of the problems we faced and mistakes we made and things we learned. Briefly, as an agenda, we'll start with a discussion of what is a language model and what does it have to do with AI anyway. And then we'll get into the design and training experience of the model and finally discuss some evaluations and pull out some takeaways. So what is a language model? A language model, or more specifically an autoregressive language model, solves the following problem. Given a sequence of words, predict what word will come next, and this prediction is going to come in the form of a probability distribution. In this example, the sequence of words to begin with is the cow went to the, and we feed that to the language model, and it produces a prediction in the form of a distribution on what word comes next. Here it thinks field is most likely, followed by barn, with some other words possible as well. That's what a language model is. No more, no less. Well, how do we use a language model to generate text, like you see in a ChatGPT or something like that? It's quite simple. We take our sequence of words, the cow went to the, we get our prediction over what word comes next. We choose a random word from that distribution, and that's the next word we generate. We append that word to the initial set of words. That's our new sequence. We feed that into the language model, get a new probability distribution, sample a new word, and so on. That's how we generate text for a language model. And that's at the core of all the large language models that we appreciate today. So language models are not new. In fact, they're at least 75 years old. Claude Shannon spoke about language models in his seminal work on information theory in 1948. He was building language models by hand, by looking through books and tabulating relative frequencies of words to build his language models. So what's changed in the last 75 years? What's special about the modern language models, which have these amazing capabilities? There's many things. I'll highlight one, which I think is very important, and that's the size of the sequence that the model can use to predict the next word. So it's not just predicting a word that makes sense at a sentence level, the cow went to the barn, sure. It's predicting a word that makes sense in the context of a paragraph or a page or a document, a large context, it would be called. And I think it's one of the main things that makes the modern models very powerful. OK, so we know what a language model is. We know how to generate text from it. There's one detail I simplified. I'll elaborate on it now. Modern language models don't actually deal with words directly. They deal with these things called tokens. A token is a sequence of characters, or these days really even a sequence of bytes. And that's what is predicted as opposed to a word. Why are we dealing with tokens instead of words? It gives us the flexibility to handle situations that words won't allow. So for example, here we have Pennsylvania spelled correctly. That's its own token. But when there's a typo in Pennsylvania with an I, if we were restricted to words in the dictionary, the language model would not know how to deal with this. But we allow arbitrary strings to be broken up into chunks called tokens, indicated by these colors, and we could still handle words with typos. Even more than that, we want to handle code. Of course, we want to handle numerical expressions. And again, if we're limited to words, that wouldn't be possible. One thing I'll call out, because I want to refer back to it later, is this is the tokenization from the GPT-3 model. And in its handling of this numeric expression at the bottom, it seems like a somewhat arbitrary partitioning into chunks sometimes, 2 digits, sometimes 3 digits. And that's something that gives us some concern in how these types of models will be able to handle numerical expressions. OK. So we know how to generate text with a language model. What does this have to do with AI? Back in 2000, around the time I was starting graduate school, in the field of natural language processing, there is a grand challenge problem called the reading comprehension problem, which we're all probably familiar with from standardized tests. There's a passage of text, there's a question, the answer to which is in the passage, and you use to produce the answer. Now, back in 2000, it was a grand challenge problem because no one really knew how to solve it. The best attempts were to break the problem into several steps and pipeline them together, and it really didn't work too well. Fast forward about 20 years to the release of GPT-3. It's about 3 years ago to the month from now. GPT-3 is a language model. We know how language models work. You feed some text in, it generates some new text. So let's take this passage and the first question and feed that into the GPT-3 language model. Generate text to see what happens. Well, it sees this passage, it sees the question, it starts generating more questions. It thinks it's looking at a test. It tries to generate more text like the text it has seen during training, and it generates the rest of a test, along with, thankfully, some answers to those questions. Now, I won't bore you with the details of this passage, but answer 1 is the correct answer to the question that we posed it. And so it seems to be able to solve this problem, but in a somewhat backwards way, right? It doesn't directly answer the question. It kind of implicitly shows that it knows the answer without kind of satisfyingly just directly saying it. Well, this was 3 years ago. And in the last 3 years, there's been a lot of work to condition models of this sort to be something you interact with in a more comfortable way, where it just directly tells you what you want to know and not just continuing things that look like documents in its training set. So this was very convincing to us 3 years ago that these models had a lot of potential. And it wasn't just reading comprehension. It was showing very interesting work on summarization and lots of things. And I feel like I don't need to convince you at this point that large language models are very powerful. I just kind of want to give you a sense that even 3 years ago, we could see that there was a lot of potential with these large language models, which is why at Bloomberg we decided to invest in this direction some time ago. OK. So what does one need to do to build a large language model? Very briefly, at a high level, I'll divide up 3 categories that one needs to consider. One is code. And by code, I don't just mean the code itself, but also all the decisions one needs to make to size and shape your model. Besides code, you need data. Data is the language or the code or whatever it is that you want your language model to learn to emulate. So collecting data is another huge piece. And finally, the compute infrastructure you need to actually carry out the training of your model to fit the language model to your data. So as we talk now about designing the BloombergGPT model, each one of those sections is going to have a lot of decisions to be made. Just briefly, I list some of the many, many things. These are already many of the even more things one needs to decide when building out their model. There's how big is it? What's the shape of it? How big is your data set? What are the low-level implementations of the pieces of your model that you're going to use for efficiency and effectiveness? There's questions of your hardware stack, not just the compute itself, but certainly the network interconnects and the data storage. All these things are very important to the eventual effectiveness of your training job. When you train a model like this, we used 512 GPUs. This is parallelized across many machines. And the optimization procedures are very complex. There are several out there that are freely available to use, but you need to choose them and set them up properly. It's someone on your team is going to have to figure out how to do that. There's numerical precision decisions. There's tokenization we discussed, data set composition. I just want to give you a sense of all the things that one needs to think about when building your own model from scratch. So we'll drill into just a few of those decisions where maybe we deviated a bit from the tradition. So at a high level, what were our design goals and considerations? So we defined success to be if we could build a model that performed about as well as what we considered our kind of cohort of models from last year, performed about as well on general purpose tasks, but we're performing state-of-the-art level on finance-specific tasks, which is the domain of our specific interest at Bloomberg. As far as considerations, we knew just from reading and speaking with people that training large language models is a very risky endeavor. All sorts of money has been spent on training large language models that didn't end up doing well and didn't perform well. So one of our main objectives in the planning was to mitigate risk. And to that end, we decided the best thing we could do is copy as closely as we could some other model that was successful and only deviate where we absolutely had to. And to that end, we chose the Bloom model from the Big Science Project, which had released all of its code and gave very detailed descriptions of its procedures. And so the Bloom model is what we used as our base. The Bloom model follows in the tradition of the GPT 1, 2, and 3 models in being it's called a decoder-only transformer model. Some people just call it a GPT-style model. We made the same. And so going forward, I'll give a few spots where we deviate from the Bloom architecture, but that's essentially what we followed. Another consideration is that we wanted to apply this to finance. And we believe that to do well on finance tasks, you need to be able to handle numbers well. Makes sense. We have some concern about the tokenizer I showed earlier in the way it works with numbers. It breaks it up into these arbitrary chunks. And I'll show you that we took a slightly different path. As far as constraints, there are many, but the ones I'll highlight is we had a set compute budget. We had access to 1.3 million hours of GPU access, and the whole project had to be done by the end of 2022. For context, the planning started kind of in early 2022, but really accelerated in the summer. Training started in September, and we got a bit of an extension. The model, we finally were done training entirely about 2 weeks into 2023. OK, so I don't want to say too much about all the things we did in our own custom tokenizer, but I'll highlight the thing that we did for numbers, which is rather than break things up into these kind of arbitrary chunks, we separated numbers into individual digits, which we thought the model would be able to handle more easily. And I'm happy to chat about this more in a Q&A at the end if you have some interest in that. Probably the thing that distinguished BloombergGPT the most from other models is our data set. We certainly made use of the usual suspects of open source data. That'd be C4, which is a massive amount of data taken from web crawls. That would be the pile, which is a rather diverse set of data, things like PubMed and code from GitHub and research papers from arXiv, and certainly Wikipedia. And we also threw in our own version of Wikipedia, which is a little bit more recent than the ones that show up in C4 and the pile. So that public data constituted about half of our training data set. The rest of the data set is our private data from Bloomberg, which we call FinPile. Bloomberg's very much a data company. And so just as part of our usual business process, we're collecting and cleaning and processing and cataloging enormous amounts of data. And we've been doing so for decades. So for this task, we gathered together data we thought would be most useful, things that were already nicely cleaned and ready to go. And we ended up collecting data starting from 2007 and coming through until summer of last year. OK. I think it's worth taking a minute to register how much data we're actually using. So I didn't give you numbers. The private data set was about 400 billion tokens, and the rest was from the public data set. So all in, 710 billion tokens of data. How much is this? Let's think in terms of Wikipedia. The English version of Wikipedia, if you drop all the images and tables and just have the text, if you were to print this out and bind it into volumes and put it on bookshelves, it would fill 16.5 bookshelves. And these are not even ordinary bookshelves. These are bookshelves that are 9 shelves tall, much taller than an average human. And if you picture these bookshelves lined up full of books. It's going to be like a whole grocery store aisle or something, right? An enormous amount of information in Wikipedia. And our training set is 200 times larger than that. So just it's really a staggering amount of information, staggering amount of data, and it kind of makes it clear why one needs so much compute power to train a language model to fit to this data. OK, so we spoke about the data set. Another major decision in building a model is how big to make it. You often have a fixed budget of compute, how many GPU hours you have to work with. That was our situation. And when designing a model, there's a trade-off. See, the amount of compute it takes to train a model grows linearly with the size of the model in terms of its parameter count, and also linearly with the number of training tokens that you have. So for a fixed compute budget, you kind of have a choice. Should I make a bigger model and train it on less data, or make a smaller model and train it on more data? So until this very influential paper was published in early 2022, the answer to that question was build a bigger model. Don't worry about the data. Most of the large models trained up until that point were on data sets of roughly 300 billion tokens, give or take. And so when people had more resources to throw out the problem, they would build a bigger model, same data set. When this paper came out, it really suggested that people were thinking about it the wrong way, and that all those large models would have done better had they used the same budget on a smaller model with more training tokens. Very influential result that we took to heart in our own decisions on the sizing of the model. So when we chose the parameters for our model, we were on the smaller side. On the bottom, BloombergGPT, 50 billion parameters, compared to what we consider our peer set. That would be GPT-3, which kicked this all off, GPT Neo X from Luther AI, the OPT66, that's from Meta, the open source model that was very forthcoming with their training logs, and Bloom would be our other peer. And you'll see that each of these models were somewhere around the 300 billion range, whereas we used our resources more towards a larger training data set than towards a larger model. OK. There are a few changes from the Bloom model that we made intentionally, some that we made unintentionally. But one I'll highlight is that we noticed the FinPile data set, our internal private data set, every item is timestamped. And we thought, well, when we actually apply this model, it seems like the most relevant data in this training set would be the most recent, because we're applying it to current problems. And so maybe it would make sense to train the model chronologically on this finance data so that when we're done, the data it had been trained on most recently was also the most recent data, and thereby the most applicable to downstream applications. And so we did that. We chronologically sorted our financial data, randomly mixed in the public data, and that was our training data set. So not, as is the convention, a complete random sort. And that was where we were when we started to train the model, version 0. So now I'll dive into some of our training experience. So what we see here are the performance loss curves for training our V0 model. On the x-axis is steps, which is you could think of as time. And the y-axis is loss, and you want loss to be small. And what's represented here is about 10 days of training. And things seem to be going well at first, but about 4 days in, the learning curve just didn't go down very fast. It's still going down a bit, but when we compared to other models trained in a similar situation, the decrease in the loss seemed much more aggressive than ours. And this is a real concern. We were only 4, 5, 10 days into training, and we expected this to go on for 2 months. If training is stopping or is too slow, this could be a real issue. And we thought about it, OK, maybe the problem is that sorting of the data. Because everything we're testing on is out of sample, is from a future time period. It's because we sorted the data, it's a different distribution of the data that we trained on. And so we're always evaluating our model on stuff that it really has, some of it may have had no chance to learn. And so maybe that's part of the explanation for the slow learning. And maybe had we continued to train this model till the end in this way, it would have worked just fine. But it was a little bit too risky for us. Moreover, we were concerned that suppose another problem cropped up. How do we ever, there'd be this confounder. How do we ever know whether it's a problem or, oh no, maybe we just hit a bad patch of training data because it's not randomly sorted. And so it seemed a little bit too, we couldn't stomach training this much longer. So we cut V0, we shuffled the data completely, as is the more standard practice, and started training the V1 model. Now, the V1 model started off rather well with the validation error decreasing nicely. Now, in the OPT model from Meta, their training logs indicated that they encountered training instability. And one thing that they monitored was this thing called the gradient norm. And when the gradient norm started to do funny things like spiking or increasing, that was an early predictor of the model training going awry. And that was something they monitored, and so we did the same thing. So here's the gradient norm over time during our version 1 training. There's at least two curves here. Keep your eye on the blue one for starters. And the graph starts again at around day 4, and things are going fine, a little blip here. And then this blue line, this gradient norm curve, kind of makes a turn and starts heading up almost linearly with these big spikes mixed in. Now, this is just textbook instability prediction, early indicator of instability. And indeed, around this time when the spikes happened, the performance was also going down. And so, luckily, we had an approach to this because the OPT team shared what they did, what their recipe was when they encountered the situation. Their recipe is rewind training to before this spike happened, shuffle your data that's coming up ahead, because maybe there's something odd with the data right there, and lower your learning rate. OK, so we did that, and then we ended up with this orange curve, which seemed to do better, but really it was just delaying the spikes and the increase. So also not great. We tried a few more things of the same style, and we still had the same problems. OK, so at this point, we went into deep debug mode, and we found a lot of things. I'm going to highlight one. This gradient norm spiking, we thought should have some repercussions in the parameter values themselves. So we looked at our model. There's 70 layers. Each layer has several components. We looked at the size of these parameters in each component and graphed them over time. And a couple lines stand out. You might be able to see. There's this line that kind of makes a left turn around time 12,500. And this line also in parallel makes this left turn going up. How odd. Both of those parameters come from the same component. It's the first layer of the transformer, and it's the layer norm. So we looked at the parameters of one of those layer norm components, the ones that start at 1. And we see this odd behavior. There's a sample of 60 of those 1,000 odd parameters. They go down, and then they make a left turn and go straight up. To this day, I don't have a definite explanation for what's happening here. I have a hypothesis we might be able to talk about afterwards in the Q&A. But at that time, we were going through the code. What could possibly be causing this? We found one bug, which was that we were doing weight decay on these weights. Weight decay pulls weights towards 0. These weights are initialized to 1, and we expect to center around 1. So that's a mistake. You don't want to pull weights towards 0 when they should be around 1. So that's one bug we found. We still didn't really understand why this was happening. And we continued our debugging process, and we found 10 things that we wanted to change. Some of these were bugs. Some of these were just throwing the kitchen sink of tricks that we had read about that could control stability. We just basically did everything we could to make the model train stably. We started over, reshuffled, new random seeds, and started again. And that was version 2. Now, the short story of version 2 is that things trained rather well for 42 consecutive days. This blue curve on the left, is our performance, is our loss. We want it to go down. It's going down fairly steadily for 42 days. And then at 42 days, that curve makes the left turn and starts heading straight back up. Not sure why. We tried all sorts of things. We decreased learning rate some more. We added dropout. We did some shuffling, all the tricks we could think of, and nothing really could get the model to consistently increase again. But you know what? We tested the model as it was on some downstream tasks. It did rather well. It was already performing at our goal level. And so we called it. We were essentially out of time anyway. We are at the end of our budget and our time constraint. And so that is the end of the story for BloombergGPT training. It's still, we have, again, hypotheses about why training didn't continue. And we could talk about that later if you like. But the bottom line was we did not even use our entire training data set. There were still over 100 billion tokens that we hadn't used. All right, let's talk about evaluation a little bit. I have the charts we can look at, but I'll just give you a high-level summary so we can get to some discussion. We considered our peer set to be the other open source models that were available around the start of our training in last year. I mentioned NeoX, OPT66, and Bloom. On the general purpose tasks, so MMLU is a big one that measures general purpose knowledge. We are the same or better than these peer set. On Big Bench Hard, which is a lot of kind of reasoning tasks, we were essentially on par. On the financial tasks, the public financial tasks, we were significantly better. One of those tasks involves kind of, it's like a reading comprehension, but it'll have a numeric table in there as well. And the question will be in some way referring to that table. And so in that task in particular, we did quite well. And we speculate or hope that that might have something to do with the fact, some combination of the fact that we're training on financial data, and we have this tokenizer that was adjusted to handle numbers. We also tested it on internal challenges, such as sentiment analysis, named entity recognition, and named entity disambiguation. We did much better on the sentiment analysis. The named entity NER, we did not as well as Bloom, but we didn't actually train on NER directly. But when we added an extra step to that task to make it more realistic, which is not only to identify an entity in text, in our case, a company, but also match it to the stock ticker, we did the best of the group. And again, we think that's because of the financial domain training data. Okay. We also tried it on this kind of a qualitative analysis. Internal to Bloomberg is something called BQL, Bloomberg Query Language. It's a very complicated language to gather and analyze data, a lot of the data on the Bloomberg terminal. It's hard to learn, and we thought, wouldn't it be great if one could just type in natural language what you wanted to do, and the BQL would be produced by this model. So you could both get your BQL and learn it and get the data you want. And the model does pretty well on this out of the box, despite not having any BQL in the training data at all. So we did this with what is called few-shot learning. We gave 3 examples of the translation between natural language text and this BQL output. And for the 4th example, we would just give the input, write output colon, and then have the language model continue to generate, and it would generate this BQL text. And this works, just anecdotally worked fairly well out of the box, which is nice. This is one of the things that we're excited to bring to the product in the future. More ambitiously, we're excited to bring something of a natural language interface to the terminal as a whole. On the left, we have an image of the terminal where we're trying to plot the market capitalization of Apple versus Microsoft. Most terminal users would have no problem with that at all. Now, if you want to change the x-axis to start, say, from another date, you might be able to find a pull-down window to do that without too much difficulty. But if you wanted to, say, add in the number of employees at each company to this chart, now it becomes very challenging to do. And this is not, it's not really a limitation of Bloomberg in particular, its interface. It's just, there's only so many things you could put into an easy-to-use interface. And sometimes you're going to need to pull in some either some power user stuff or maybe a natural language interface would be the best way to get to it. Okay. So as far as takeaways, here's some advice. It's actually It's actually obvious, but in the heat of the moment, when you have a lot of time pressure, you might forget to do it, as we did. And so my advice to you is the following. If you endeavor to build a giant language model, work your way up. Don't start with the biggest model. Start small and work your way up. Not every problem you'll encounter will show up at a smaller scale, but a lot of them will. And it's worth the time, because the cost of training your smaller models is minuscule compared to the cost of training your large model, and it's worth working your way up. It's not a huge additional expenditure of money, and the time will be well spent. In the same vein, if you're inspired to innovate to change what someone else has had success with, which you almost certainly will be, because if you want to do exactly what someone else would do, you would probably just use their model, run your experiments at a smaller scale before you start. Because otherwise, you may make your change, you may get lucky and it works, but you'll never really know if that change made things better or worse. So run an experiment so you can really learn something at a smaller scale. And then you'll have more knowledge to take away. As far as conclusions, from our point of view, this was very much a research project. And I guess the first question of the project is, could we do it? Could a relatively small team of folks build this model, this large language model, and have it work on par with the GPT-3? And the answer is yes, you can. If you have the compute resources and you have the time and patience, it's not necessarily easy, but it can be done. And the second question that was essentially open, and I think we resolved, is can you mix domain-specific data with general-purpose data and end up with a model which can kind of do both? It does well on general-purpose tasks, and it also has a deep knowledge of the domain that it was trained on. Okay. So with that, I'd love to say just 3 more directions that we're thinking about, and then open it up to questions. So one is, did we lose some efficiency in training by being too cautious on the stability stuff? Maybe we had lowered the learning rates too much, and maybe that's why, for example, we stopped learning. That's an open direction for us to investigate. The second thing, which I'm sure a lot of you are wondering, is, did we really need to train a giant model from scratch? Could we have taken an open source model and fine-tuned it on our data? It's a great question. I guess the one thing that makes our scenario much different than traditional fine-tuning scenarios is that our kind of fine-tuning data set was 300 billion tokens. Most fine-tuning tasks are much smaller fractions of the full training set, so it's a little bit different. And finally, there is that last gap between a model that just continues text to make it look like it's training documents and a model that directly answers your questions like ChatGPT or Bard do today. And that's what we're in the process of right now with our model. Okay, with that, I'd love to open the floor to any questions. There's a microphone over there. If anyone has anything, I'd love to just chat. Yeah, the microphone is over there. I guess she can then come over to you, or you can meet them.
So you built a decoder-only model.
I can't hear you so well. Again?
You built a decoder-only model. I'm curious if you considered, or if you are considering, building an encoder model or an encoder-decoder model or any other type of model to feed it through maybe other workflows than just typical kind of prompt output.
So the question is, if I understand correctly, did we consider other styles of models such as an encoder-decoder model? Very much so. There's early evidence that in some ways encoder-decoder models are better than the style of model that we use, which is a decoder only. That said, there's very few examples of very large encoder-decoder models that have been successfully trained. And so again, in the line of risk mitigation, we weren't going to go down that route. And that was a year ago, and still you don't see many encoder-decoder models at large scale. What you do see are decoder-only models, as we did, but with the training objective that's closer to this denoising objective that people also often use on like BERT-style or encoder-only models. That's definitely an avenue of interest for us that when we get to our next version of the model, we'll be running small-scale experiments in that direction. Yeah. Another question over here. Oh, back there, okay.
Hi, thanks for your demo. I have a question. I wanted to know how did you decide to choose which data set to mix with your proprietary Bloomberg data set? And did you see any impact of like mixing different types of open source data sets?
I think there were no concrete experiments run to make that assessment. We were going based on essentially anecdotal evidence or reports we read describing certain data sets as more clean and having gotten better results. So we tried to follow previous projects' success in what data sets that they chose. That's kind of how we did it. But yeah, go ahead.
Yeah. In your presentation, you have shown different tokens in different colors. So how would this model depend upon token size?
Again, say it again, how does the model what?
In your talk, you have shown different tokens in colors, right?
Yes, different tokens.
So
Yeah.
what is the maximum token length, and how this model would be better? Like, can I make it better by fixing token size or by changing token size?
By token size, you mean how many bytes or characters are in each
Exactly,
token?
yeah.
Okay. Okay, so there's no limitation in the length of the maximum token allowed. In the earlier tokenizers that we deviated from, they constrained tokens to contain at most one word, so one string of contiguous characters of the same type. We didn't make that constraint, and some of our tokens were quite long. Some of our tokens had multiple words. Where you are limiting your tokenizer is how many different tokens you have. So before you start training your model, when you build your tokenizer, you have a complete list at that point of tokens that are allowed. And there's another decision point of how many tokens you have. Traditionally, the GPT-2 style model has like tokenizer has like 50,000 tokens. We had 130,000 tokens. We thought that might work better for various reasons. But that's the main constraint, is how many tokens. Questions here?
Thanks for the great work. So my question is, in finance, usually documents and reports could have other types of, other formats of data, not just raw text. There could be tables, there could be visualizations and charts. So my question is, have you considered expanding these large language models to become multimodal?
Yeah, definitely on our mind. There's various ways to do it. One would be to try to incorporate vision, so it can you could have some vision inputs of tables or graphics. Another way would be to use a different process to somehow convert, images might be hard but possible, but tables would be very reasonable, to convert things like tables into a tokenized format. And so we're definitely interested in both of those directions. For this model, we only dealt with data that was, in some sense, already ready to go, which didn't have didn't incorporate those pieces of the data. Yeah, that's a nice question. There's a question up here.
Yeah, I have two questions. First, it's regarding tokenizing. You said that the smaller models are preferred with fewer parameters, and I think tokenizing, of course, has like some kind of relation to this, to make models smaller. So what were your strategy to tokenize? Because I found some words were splitted in the example you showed, and there were some words combined, like bigrams. So what was your strategy in that to make your model smaller? And also my second question is regarding BQL, and what was its application? If you elaborate on that, thank you so much.
I would just say that we're coming up on the 40 minutes in just 40 seconds, and so I might have to take myself off stage before we're done. But as far as the tokenizer, we allowed multi-word tokens, whereas most others don't, because we thought it would be interesting to try. It's not a decision we necessarily would repeat. It is true that using more tokens increases the number of parameters you need at the embedding layer. And we were just trading that off against the efficiency in terms of number of tokens it requires to encode information. And the more efficiently the fewer tokens you need to use, the less of your context window you need to use in your model, which gives you more of your context window for generation. I'm happy to talk offline in more detail. Thank you all for your time. I think it was great chatting.